Thank you, Dr. Charu. So, good morning, all. So, today I will be giving an overview of applications of various satellite data, particularly the satellite radiances in numerical weather prediction system. So, before going to the satellite data, so why do we need the satellite data? So, as you know, that we have many conventional observations. Conventional observation in the sense it is in situ observations like upper air observations and surface observations also. So here the upper chart, it shows the upper air observations, that is the radio sonde, then pilot balloons, wind profiler, everything. So you can see from this figure, most of the upper air observations, it is means mainly over the northern hemispheric land region. And if you see the southern hemisphere, especially over the ocean and over the land region, the number of observations are very less. And if you come to the bottom panel shows the surface observations, that is the in situ surface observation. Here also you can see that we have a good coverage of observation, but the problem is it is surface observation and it is only single level observation. So in this case, so we have to get more observations over the oceanic region and the remote locations where the conventional observations are not available. So then in that scenario, we need more observation, then satellite can play the major role. So that's why we need more satellite observation for the numerical weather prediction. And I think all the participants may be knowing the different types of satellite orbits. So we have the polar orbit, then we have the geostationary orbit, and we have the inclined orbit. For inclined orbit examples, that satellites in inclined orbit examples, one of this Indian Indo-French collaboration satellite, that is Megatropics, that was in the 20-degree inclined orbit. And another satellites in the inclined orbit are that GPM and former that TRMM, that these satellites are in the inclined orbit. And another orbit is the highly elliptical orbit. Highly elliptical orbit means, as you know, the geostationary satellite, that we can scan a particular area continuously, that 24 hours, 24 by 7, or throughout the year we can scan the particular location. But it is not true over the polar region. So polar region, we don't have the that station time more for a particular satellite. So then in this type of highly elliptical orbit, we have more stationing time over the polar region, and we get continuous observation over the polar area. So that's what the high importance of highly elliptical orbits. So these are the different types of orbits, and we do have many meteorological satellites in these orbits also. So if you see the WMO's meteorological satellite network, so it includes the satellite from almost all the space agencies. So here you can see this is the meteorological satellite coverage, or the meteorological satellite operated by different agencies. And this is the geostationary ring we can see. So here we can see that over India, that means we have many satellite, geostationary satellite having coverage over India. Like if you see the Himawari, now Himawari 8 is replaced by Himawari 9 by Japan, and GeoComSat, that is operated by Korea. And we have the FI4 from China, and we have our own satellite INSAT 3D and 3DR, and we have one more satellite Electro, that is the Russian satellite. So if you see over this region, there are many geostationary satellite which are having coverage over the Indian region. And coming to this side, we have the Meteosat 10. So that is the geostationary satellite by European Space Agency. So Meteosat 10 and the Meteosat third generation satellite. That Meteosat, that IODC, that is the Indian Ocean Data Coverage Service, that provides data over the Indian region. And coming to the US side, we have the goes east and goes west. So this is the geostationary satellite ring. And when we see the polar, so we have many satellites in the polar orbit also, like TRMM. Right now TRMM is not there. Then we have the GPM. Then FI3 series of satellite from China. Then METOP satellite from European Space Agency. and SNPP and NOVA series of satellite from US Space Agency, and we have the A-Train, that is the afternoon equator crossing time series of satellite. And in the highly elliptical orbit, we have the Arctica from Russia and PCW from Canada. So this is the currently available meteorological satellite network in different orbits. So then if you see the satellite data, what are the different data we are getting from satellite, mainly for the NWP application purpose. So this is the AMVs. AMVs means it is the atmospheric motion vectors derived from the satellite images. And here you can see that this is the full geostationary coverage, and we have the AMVs over the polar region also. And we have the radiances mainly from the polar satellite also, and from the geostationary as well. So this is the radiances, and this is the scatterometer data. So scatterometer, it is mainly the sea surface temperature on board the scatterometer instrument. So here we have shown only the SCAT, but right now we have the scatterometer data from the recently launched OceanSat 3 as well. And another observation is the GPS-RO, that is the global positioning, that radio occultation data. So that also we have the global coverage, good coverage of GPS-RO observations. So these are the main type of satellite observations we are mainly using in the NWP assimilation system. And today we will talk more about the satellite radiances. So when you see that the satellite observation, what I think these things, these fundamental things you may be knowing well, but still for the completeness, I'm just covering this part. And satellite can measure only the outgoing thermal radiation from the atmosphere. So we have the incident solar energy, and some of the energy is reflected back. And whatever the energy that is Earth is emitting, that is what satellite is seeing. So then there may be some reflection, absorption, scattering, all those things. I think in the previous lecture, sir might have told all this information, what are the different means properties, or the absorption, emission, scattering, or those things, what is happening in the atmosphere, and what is depending on the absorption, emission, or scattering, what properties we can measure. Those things I think it might have covered. And if you see, what do satellite instrument measure for the NWP purpose, what we need, as you know, the for NWP means model or NWP governing equations, what we have is the meteorology, geophysical variables like temperature, humidity, wind, or the ozone or carbon dioxide, those variables only. We don't have any radiance in that means governing equations. But what satellite can measure is the energy or the radiance it is reaching at the top of the atmosphere at a given frequency. So how do we use this radiance? That as such radiance, we don't have any variable in our NWP equation. So how can this radiance is related to the geophysical variables? So if you see, the measured radiance is related to the geophysical atmospheric variables like temperature, humidity, and wind through radiative transfer equation. So when we talk about the radiance, satellite radiance assimilation, or the satellite brightness temperature assimilation, the main factor is the radiative transfer equation. So this is the simplified form of the radiative transfer equation. So we can see that the measured by the satellite, what is the energy or the radiance measured by the instrument, that is L of at a particular frequency, L of V. Then we can see we can describe our atmosphere in our own way. So if you want to include the temperature variation, if you want to include the surface emission, reflection, scattering, or cloud, rain, all those things we can include. And if you don't want to include the surface properties, we can remove that also. So that is as per our convenience, what we want to do. So the description of the atmosphere may be different for different applications. So this is the description of the atmosphere. So we have the temperature term. So this is from the Planck source term, depending on the temperature of the atmosphere. And we have the absorption term, that is the absorption in the atmosphere. And we can include the surface emission term, surface reflection and scattering term. And if you want, we can include the cloud, rain contribution. And if you want to include more constituents, trace gas, all those things also you can include. So this is our representation description of the atmosphere. So the radiative transfer equation we are describing like this. So what it is doing, so we have the measured radiances from the satellite, and we are defining our atmosphere like temperature term, surface emission term, reflection, scattering, whatever we want to represent in that one. And suppose if we have the means given the state of the atmosphere, so we know the state of the atmosphere, we know the how much surface emission is there, how much surface reflection and scattering is there, and what is the temperature and how the temperature is varying, the temperature profile is also there. So given the state of the atmosphere, we can calculate the radiance measured by the satellite. So if you know the complete state of the atmosphere, we can calculate how much the energy can reach up to the top of the atmosphere, or how much energy the satellite instrument can see. So this is known as the forward problem. Forward problem means the state of the atmosphere is known, and we can compute the radiance reaching at the, or the energy reaching at the instrument. And so for that, so suppose in the case we have the state of the atmosphere. So state of the atmosphere, suppose we are considering only the temperature variation. So the state of the atmosphere is the temperature profile at a particular location. And we have to use the radiative transfer equation. And we have the standalone radiative transfer models. So you may be many of you may be using WRF model. So in the WRF model, there is two options for the radiative transfer model. One is the RT-TOW and one is the CRTM. So there are many other standalone radiative transfer model also. So you can use this radiative transfer model as standalone and as part of your model also. So if we have the model state, that is the temperature, or the atmospheric state, that is the temperature profile of the atmosphere, you can use the radiative transfer model and you can compute the radiances. So this is the forward problem. So that what you know is the conditions of the atmosphere or state of the atmosphere, and you are calculating what the satellite can see. So this is the forward problem. And suppose you are whatever you are getting is the satellite measurements. So the energy reaching at the satellite, or the energy reaching at the satellite instrument, is the given the radiance. So you have the radiance. So then you next condition is you have to can compute the state of the atmosphere. So in that case, it is the inverse problem. So the radiative transfer equation we can use for both forward problem and inverse problem. The forward problem means you know the state of the atmosphere and you have to calculate the energy. The inverse problem is you have the energy and you have to inversely calculate what is the state of the atmosphere. So this is the inverse and forward problem. Okay, so when you come to the numerical weather prediction, so the forward problem is the observation operator. So observation operator means the radiative transfer equation for the case of satellite radiances, the observation operator is the radiative transfer equation, because we don't have what exactly the radiances or the brightness temperature in the NWP governing equation. So from the model state or the model variables, we have to compute the equivalent brightness temperature that can be that is measured by the satellite. So then only we can compare the observed radiance and the model simulated radiance. So why this is important? This is important because that we have to, before assimilation, we have to compare the model state and the observed state. Then we have to compute what is the O minus B value. So if the O minus B is higher than a specified value, we cannot assimilate those observation in the assimilation system or in the NWP system. So the observation in the case of satellite radiances, the radiative transfer model or the radiative transfer equation acts as a observation operator. So in the case when we consider the radiative transfer model as an observation operator, it is a forward problem. So when after that you simulate and you do the quality control of all the observation, then we have a set of observation that we can assimilate. So assimilation means we have to minimize the cost function. So when we minimize that cost function, then we have to again compute back from the radiance or the brightness temperature to the model state variables. So there we have the radiance and we have to compute back to the model state, that is the temperature, humidity, those parameters we have to compute back. So in that case, it is a minimization problem. So minimization or the inverse problem. So if you consider the observation operator is the forward problem and the data assimilation or the minimization or the retrieval algorithms, these are the inverse problems. So this is the main two applications of radiative transfer in the radiative transfer equation in the NWP assimilation. So observation, operator, and the minimization. So forward and inverse problem, both we use in the NWP assimilation. So then how can we simplify the forward and inverse problems? So for simplifying this thing, we have to do some channel selection. So then we already seen that means whatever the satellite measures is the energy reaching at the top of the atmosphere, and this energy depends on the frequency. So that we have seen in that Planck's equation or the radiative transfer equation, the energy at a particular frequency. So by deliberately selecting radiation at different frequencies means it is in different channels. Satellite instrument can provide information on specific geophysical variables for different regions of the atmosphere. So in general, particularly for the NWP, so we have the atmospheric sounding channels. That is mainly the atmospheric sounding channels are the passive instrument. And we have the surface sensing channel, that also surface sensing channel we have both in the passive and active instrument. But even if we are telling that we need the frequencies or channels in the atmospheric sounding and surface sensing active and passive instrument, but usually the satellite instrument is the combination of all the three. So atmospheric sounding channels will be there, and along with that surface sensing active and passive channels may also be there in the same instrument. So I heard that the previous lecture by Dr. R.P. Singh, that he has mentioned about those surface sensing channel, all those things, how they retrieve the carbon dioxide and different trace gases, all those things. So this combination of these different channels, it is not only for atmospheric means NWP assimilation, it is for other applications also. So basically, normally the satellite meteorological satellite instrument will be a combination of atmospheric sounding and surface sensing channels. So I think you all may be knowing about the atmospheric window. So atmospheric, this is the infrared atmospheric window. We can see those. So x-axis is the wavelength in microns and the y-axis is in the transmittance. And here we already shown these absorbing molecules. What are the different absorbing molecules available in different regions. So atmospheric transmittance, it depends on the air mass penetrated by rays as well as on the amount of water vapor and dust in the air. And it varies for radiations of different wavelengths. So, smaller the atmospheric absorption and scattering of light, the greater the atmospheric transmittance. So here you can see that some of the wavelength ranges, the atmospheric transmittance is above 80. So that smaller, the atmospheric absorption is smaller in this particular region. So in these cases, the atmospheric transmittance is very high. Then if you see the atmospheric window, it is a range of wavelengths in the electromagnetic spectrum that can pass through the Earth's atmosphere. There are atmospheric window for optical, infrared, and radio waves, and comprise of three main atmospheric windows. This is only for whatever here it is shown. It is only for the infrared atmospheric window. So as we discussed in the previous slides, we have the atmospheric sounding channels. So suppose if we want to select the sounding channels, so we have to select those channels where the transmittance is minimum. So this here you see that here in the 7 microns, that the transmittance is nearly 0. So that means whatever it is the emitted radiance, it is absorbed in the atmosphere. It's not the transmitted to top of the atmosphere. So it is mainly absorbed in the atmosphere. So we have to select those channels or those frequencies where the contribution from the atmosphere is maximum. So if you see in this region, the contribution from the surface is maximum because we have the transmittance of 80% in these particular wavelengths. But in this particular range, if you see, the transmittance is nearly 0. So that means the most of the contribution is coming from the atmosphere, not from the surface. So here another channel between 14 and 15 microns, and we have another channel between 4 and 5 microns. Like that, we can select the channels so that where the maximum contribution from the atmosphere is coming. So for the atmospheric sounding channels, we have to select those frequencies where the contribution from the atmosphere is maximum. So again, we have to analyze our radiative transfer equation. So this is the radiative transfer equation. And for the atmospheric sounding channel, what we have to do, we have to assume that there is no contribution from the surface for that particular frequency. So there may this assumption may not be correct always, but we can assume that surface contribution is very nearly nearly nil kind of thing we can assume. But selecting channels where there is no contribution from the surface. So if we select channel where there is no contribution from surface, there is no surface emission, there is no surface reflection or scattering. So we have only the contribution from the atmospheric part. So this only in the radiative transfer equation, only this term remains. So this is how we select the atmospheric sounding channels. So for examples of atmospheric sounding channels are AMSU A, channel 5 and HIRS channel. So as we already told that the atmospheric sounding channel, it can be in the IR region or it can be in the microwave region also. So this AMSU A, it is in the microwave, that is it's the 53 gigahertz region. And HIRS channel told it is in the IR region. So it is in the 6.7 micron. So in the microwave region also we have the sounding channel, and in the IR and water vapor region also we can get the sounding channels. And coming to the surface sensing channel. So surface sensing channel means where the contribution from the surface is maximum. So we have to select those regions or those area or those particular wavelength or frequency where the contribution from the surface is maximum. So you can see that if we select some channels in this region of wavelength, the surface contribution will be maximum. So similarly in this region. So again the same equation that we are assuming that it is only surface sensing passive. We are not considering the scattering. It is only the passive surface sensing channel. So there is no contribution from atmosphere. So this is the assumption. So we have to select those channel where there is no contribution from the atmosphere. And there is no scattering. So there is no contribution from the passive channel or the scattering. So only the surface emission will come. So this is the surface sensing channel passive. So for examples of surface sensing channel passive channels are SSMA channel. So channel 7, it is again in the 89 gigahertz, it is in the microwave region. And similarly HIRS channel 8, it is in the 11 microns. So if you remember in the previous cycle, previous slide, I showed you that HIRS, it is having the HIRS channel 12, that is 6.7 micron, that is an atmospheric sounding channel. So again here in the surface sensing channel, you can see there is HIRS channel 8, that is 11 microns, that is in the surface sensing channel. So HIRS is one instrument, it is having both atmospheric sounding channel and surface sensing channel. Similarly, this SSMI is also, we can see SSMI is only imager, but there is another instrument SSMIS. So that is imager and sounder combination. So we have the surface channels and also the sounding channel. So the same instrument can have both the atmospheric sounding channel and the surface sensing channels also. So when we come to the surface sensing channel active, so mainly it is in the microwave region. So we may not have in the IR region. So here, there only we have to, if it is active, we have to consider the reflection and the scattering part. So other terms we have to neglect. So we have to select those frequencies where the contribution is maximum from the reflection and the scattering. So examples are the scatterometers. So almost all the scatterometers are active. So OSCAT, that is the Indian ISRO's scatterometer mission. So that is one of the example of the surface sensing channel active. And if you, so we have seen that there are different type of channel: atmospheric sounding channel, surface sensing channel, those things. And then what type of channels are most important for NWP? For us, when we talk about the NWP assimilation, so which channels are more important? So for NWP, atmospheric temperature or the atmospheric sounding channels are more important. So in the atmospheric temperature sounding, so we have the in the radiative transfer equation, what is the assumption that that we have to choose those frequencies in such a way that the contributions from the surface is minimum or zero. So the term, the radiative transfer term equation, it will reduce to only the atmospheric term. So here we define a function that h of z, that is the absorption term, that dou t by dou z. So dou t by dou z, that is it is with respect to height. How the absorption is changing. So that we are assuming means making as a function that h of z. So then this h of z is the when the primary absorber is a well mixed gas with known concentration, it can be seen that the measured radiance is essentially a weighted average of the atmospheric temperature profile. So the measured radiance L of the particular frequency is the weighted average of atmospheric temperature. So this is the Planck's term. So there we have the temperature term. So it is the weighted average of the temperature profile. And this function, the function we are using for weighting this one, so that is known as the weighting function. This function is that defines the vertical average is known as the weighting function. So in the case of satellite atmospheric sounding, the weighting function is very important. So the weighting function can be of different types. So ideal weighting function is with a delta function. So the delta function means only one particular level is sensitive, and it can be a boxcar function. In the boxcar function means it is sensitive between two levels, or this box type kind of thing. But in actual case, the weighting function is neither delta function or nor boxcar function. So the real atmospheric weighting functions are like this. So we have the frequency and the absorption. Then we have the different frequency ranges. So nu 0, nu 1, nu 2 are the different frequencies. And depending on where the absorption is maximum, where the contribution from the atmosphere is maximum, the weighting function varies. The shape of the weighting function will be like this. So here the particular frequency nu 0, nu 1 and nu 2. So here we can see that depending on the frequency or the channel selection, we have different weighting function we are getting. And if you see the weighting function where it peaks maximum, so from the weighting function means it contributes from that it is again the averaging of the absorption averaging over the atmospheric column, but the maximum contribution is from a particular region of the atmosphere. So but for this particular frequency nu 2, it is peaking at maybe around 600 or 500 HPA. So the maximum contribution from this particular region of the atmosphere. And for the frequency nu 1, it is peaking at a different level. So we have, when we select the different frequency, we get observation or the maximum information from different layers of the atmosphere. So what is the weighting function? If you see the weighting function, so if you see in the bottom region, we have a lot of radiation emitted from the dense lower atmosphere, but very little is survived to reach at the top of the atmosphere. So because most of the energy or the radiation emitted from the surface, it is absorbed by the means in the atmosphere. So whatever the maximum energy, it is lot of radiation emitted from the surface, but whatever it reaches to the top of the atmosphere is a very little amount of that. But if you see somewhere in the middle, there is a balance between the energy emitted and reaching at the top of the atmosphere. So somewhere at some level, there is an optimal balance between the amount of radiation emitted and the amount of reaching at the top of the atmosphere. So this is the maximum energy the satellite is seeing. But the satellite sees from the lower atmosphere and upper level also. But the maximum energy it sees from the level at which there is the balance, that there is a balance between the amount of radiation emitted and the amount reaching at the top of the atmosphere. So here also we can see that in the higher in the atmosphere, very little radiation is emitted, but that most will reach at the top of the atmosphere. So this is the shape of the weighting function, and it determines from which portion of the atmosphere we are getting the satellite is seeing the maximum information. So if you see, this is for particular channel, and if you see another wavelength, you can see the maximum information may be reaching from this particular region where it peaks. So like that, we have to select different channels or different frequencies so that we can probe the atmosphere in different vertical levels. So like this particular weighting function, the maximum information from maybe from this particular level, that may be around 850 level. So we have to select the frequencies in such a way that how to probe the atmosphere. So if you want that means information from 100 HPA, 500 HPA, or 250 HPA, like that. So we have to choose the channels in such a way that the satellite sees the maximum information from that particular region of the atmosphere. So the real weighting function, if you see, this is for AMSU A, the weighting functions we can see here. So AMSU A is having 15 temperature channels. So we here all the channels are not shown here. So here you can see that these channels, this arrow shows the channel where the channel peaks. So you will get the information from these different levels of the atmosphere, like 700 HPA, 650 HPA, like that, different levels of the atmosphere. So when we get more information from different levels of the atmosphere, you can make the temperature profile, and or if it is humidity sensor, you can make the humidity profile also. So then by selecting a number of channels with varying absorption strengths, we can sample the atmospheric temperature at different altitudes. This is how we get from the atmospheric sounding, we get the the profiles. So these are some of the examples of real weighting functions. AMSU A, we have 15 channels. So AMSU is in the microwave region, and HIRS, it is the high resolution infrared sounder. It is having 19 channels. So you can see that the shape of the different weighting functions, and it is picking at different levels of the atmosphere, and so we are getting the information from different levels. So this AMSU A and HIRS, if you see, these are multispectral, like that. The number of channels are limited, and we have the hyperspectral instruments also. So hyperspectral means the number of channels are more than 1,000. So IIRS and IRC are two of hyperspectral instrument that currently we are using in the NWPS simulation. So IIRS, we are having 2,378 channels, and ERC, if you see, we are having 8,461 channels. So even if you are telling we are having 2,000 plus channels in IIRS and 8,000 plus channels in ARC, we are not using all the channels, because all these channels are not for NWPS simulation. So whichever is sensitive to that atmospheric temperature or humidity, or some of the atmospheric constituents, those channels only we assimilate in the NWP systems. So being said this, that these are the different that instrument, how do we use in the NWP. So mainly we have to do the channel selection. So channel selection in different levels of the atmosphere, depending on the information we are getting from different parts of the atmosphere. We have to choose the frequency. So then we have to find out from which level the maximum information is coming, and those information we can put in our NWP assimilation systems. So right now at NCMR WF, we are using many instruments from LEO and GEO. So these are here I have listed some of the instruments we are using in our operational assimilation systems. So ATOS is the Advanced TIROS Operational Vertical Sounder. So we are using ATOS instruments from the NOVA 18, 19 and METOP series of satellite. So if you see ATOS is a combination of three instruments, that is HIRS, High Resolution Infrared Sounder, AMSU A, it is Advanced Microwave Sounding Unit, and AMSU A is mainly for the temperature channels. And similarly, we have AMSU B or MHS, and this is for humidity channels. So this ATOS, it is a combination of three instruments: HIRS, AMSU A, and AMSU B. AMSU A and AMSU B are microwave instrument, and HIRS is the IR, operating in the IR region of the spectrum. So another one is the AMSR2, that is the Advanced Microwave Scanning Radiometer on board GCOM W1. This is the Japanese satellite. And this AMSR2 is an imager, and here also it is in the microwave region of the spectrum. Another one is ATMS. ATMS is a sounder, so Advanced Technology Microwave Sounder. So ATMS, we have ATMS instrument on board two satellite, that is the SNPP and NOVA 20 satellite. And right now, recently, NOVA has launched that NOVA 21 also. So we have the ATMS instrument on board three platforms like SNPP, NOVA 20 and NOVA 21. And SSMIS is the Special Sensor Microwave Imager Sounder, and this is also owned by US, but the Defense Meteorological Satellite Program. This is their defense satellite program of US Then another one is the GMI, that is the Global Precipitation Mission, GPM microwave imager. So if you see the first list, these mainly almost all these instruments are working in the microwave region of the spectrum, except this HIRS, that is in the infrared region of the spectrum. So this is the multispectral LEO. And when we come to the multispectral, hyperspectral LEO, we have ERC. So hyperspectral means we are having more than thousands of channels. So ERC is infrared atmospheric sounding unit. It is onboard METOP series of satellite. Currently we have METOP B and METOP C ERC. And we have AIRS, that is the atmospheric infrared sounder on board Aqua satellite. And CRIS is the cross-track infrared sounder on board SNPP and Nova 20. So I already told that ATMS, it is the advanced technology microwave sounder on board SNPP and Nova 20. So we have one microwave instrument on SNPP and Nova 20. Similarly, we have one hyperspectral instrument also on board the same satellite. So CRIS and ATMS, these are both are in the SNPP and Nova 20 and Nova 21 platforms. So that means in the same satellite, we can launch different instruments that for the meteorological studies or meteorological assimilation. So ATMS and CRIS is an example. So it is both the instruments, that ATMS is the microwave instrument and CRIS is an infrared instrument. Both are in the same platform. So these are the hyperspectral LEO. Coming to the geostationary satellite, we don't have any hyperspectral data from the geostationary satellite, but we have one from China, but we are not assimilating those data. Then now that European agency and NOVA also planning for hyperspectral in the geostationary satellite. So then insert the geostationary multispectral, it is we are operationally using insert 3D and 3DR imager and sounder. So insert 3D and 3DR both are having imager and sounder, 6-channel imager and 19-channel sounder. And both this data, I think some quite time back, the insert 3D sounder, it stopped working. But right now we are using insert 3D imager and insert 3DR imager and sounder radiances in our assimilation system. And SEVRI is spinning enhanced visible and infrared imager on board Meteosat series of satellite. So that also we are using in our assimilation system. And we have the advanced imager also, AHI advanced Himawari imager and ABI advanced baseline imager on board GOES series of satellite, and AHI, it is the Japanese thing that on board Himawari satellite. So these are the some of the satellite instruments or the satellite radiances data we are using operationally in our assimilation system. So this is again that from where we are getting the data. So ATOS, ATMS, AMSR2, GMI, SSMAS. And when we talk about Indian satellite data, so we were having good quality data from megatropics. But right now it is not operational, that life period is over. So almost all the leading global operational centers, they have used SAFIR data. The SAFIR is the microwave sounder on board megatropics. SAFIR data operationally in their means global assimilation system, and they have reported that positive impact of this data in the assimilation system and analysis and forecast. And right now, ISRO has launched one new satellite that is on experiment basis, that is the Microsat 2B EOS 7, that is the millimeter wave humidity sounder. This is a follow-up mission of SAFIR or the megatropics, and it has those channels similar to SAFIR also. I will show some slides on that results also. Then we have the scatterometers on METOP B and other satellites. Like that ASCAT scatterometers from NOVA Nestis and UMedCast. And we have the OceanSat 3 scatterometer data also. Since June, we NCMRW started receiving the OceanSat 3 scatterometer data from NRC. So that also we are assimilating in our operational systems. So if you see the data reception global, we do the assimilation and 4 assimilation cycle, 6 hourly intermittent assimilation cycle. So 0, 6, 12 and 18 UTC. So then if you see the top panel, this is the coverage of the data during 0 and 0 and 12-hour assimilation cycle. So this is mainly I'm showing the microwave data coverage. So ARMSU-A, ARMSU-A, MHS, then ATMS, SSMIS, GPM, all those things are there. And if you see that we are showing wherever we are coverage over the India and the surrounding region from this polar satellite. And this is the coverage. The bottom panel is the coverage during 6 and 18 assimilation cycle. And all this data we are getting through NOVA and EUMETSAT. And if you see what is the impact of this data in our assimilation system. So this is the forecast impact of various type of observation in our assimilation system for the last 4 years. That is from 2019, 20, 21 and 22. So here you can see that the major contribution is coming from ETOS. ETOS means again it is a combination of 3 instruments, IIRS, then ARMSU-A and ARMSU-B. So here you can see that for different years that it is shown in different color, 2019, 20, 21 and 22. So irrespective of the years, that the major contribution is from ETOS. And the next one is the contribution is from ERC. Then the satellite wind. The TEMP is the in situ radio Sunday observation. So the conventional observation is also playing a major role in reducing the forecast error. So, but basically, if you see the satellite instrument, the satellite observation plays a major role. That mainly the ETOS and ERC. ETOS is the multispectral, the combination of 3 instruments, and ERC is the hyperspectral with 8,000 plus channels. But one more thing here we have to remember. So for ETOS, we have minimum 4 satellite. We are getting the ETOS data from 4 satellite, 4 platforms, and ERC data we are getting from 2 platforms, that is METOP B and METOP C. So if you see the microwave radiances, so here I have marked those microwave radiance which is contributing in reducing the error. Here you can see that ETOS is the maximum. Then it comes the ATMS, then the AMSR, then GMI and SSMIS, FI3D, like that. So Saphir also, if you see in 2019 and 20, we have the Saphir data. So after that, I think by February 2020, that the data, it become discontinued. The data discontinuity was there, but still we can see that Saphir data also helping in reducing the forecast error, maybe to 2 to 3% of error reduction due to the Saphir data assimilation also. So what we meant to see from this slide, that the data are very important for almost all the data are very important for the NWP assimilation. And all the data play a major role in reducing the forecast error and the analysis forecast error in the different meteorological variables. So that mainly the satellite observation, like satellite microwave observation, the brightness, temperature or the radiance, it is playing a major role in reducing the error in the forecast. So if we see the contribution from India, so microwave satellite, mainly as I mentioned that the megatropics was one of the mainly that majorly used Indian satellite by almost all the global operational NWP centers, and it was a joint Indo-French satellite launched by the Indian means PSLV C-38 on 12th October 2011, and it is as when we discussing the different types of orbits, this megatropics was positioned in a highly inclined orbit, equatorial plane of 20 degree at a height of 867 kilometer above the Earth, so as to orbit the tropical region, that is between the 30 degrees south to 30 degree north, and nearly 14 to 15 times a day. So in megatropics, we were having different payloads. So the payloads were there was a microwave radiometer Madras, and unfortunately the radiometer stopped working maybe after 2 months of launching, so we couldn't use the Madras data, or we couldn't exploit the Madras data to see what is the impact of this data in the NWP assimilation. And another one is the microwave humidity sounder, that was Saphir, and we used this data exhaustively in our NWP assimilation system, and we got very good positive impact due to the assimilation of Saphir data. And another payload was Skyrab, that is not for NWP purpose, it is only for the radiation budget computation kind of thing. And there was radio occultation sounder also. So in the beginning we discussed that radio occultation data, that is the GNSS-RO data. So ROSA was one of the payload onboard megatropics. So that data also we have used in our NWP assimilation system. So this is when you compare the Saphir data with similar instruments like Saphir, almost all the channels are in the 183 gigahertz. So that is in the water vapor absorption region of the spectrum. So here, if you see, you can see the water vapor absorption, that you have some water vapor lines here around 20 gigahertz, but you have another one around 183 gigahertz. So here that this 183 gigahertz, it is the high peaking. So high peaking region we can get from this 183 gigahertz channels. And if you see for the weighting functions, as we explained in the previous slides, so the Saphir is in the 183 gigahertz region. So we have similar channels in the 183 gigahertz region from in MHS and ATMS also. So if you see, these are the weighting functions of three instruments, the MHS, Saphir, and ATMS. And what is the importance, or what is the uniqueness of Saphir is the lowest peaking channel of Saphir. So that is the 183 point plus or minus 11 gigahertz. That was not present either in MHS or in nor in ATMS. So that the lowest peaking channel of Saphir is the unique channel in the megatropics instrument, and that contributed that majorly in reducing the error in the mainly the lower level forecast error. So that was one of the uniqueness of Saphir instrument. And we have done some analysis of the comparing those channels, Saphir and similar instruments, similar channels from MHS and ATMS, and we found that Saphir is super over that MHS and other instruments. And since I told that we could not use the Madras instrument because it was an imager, so it stopped working. We did some experiment in combination with AMSR. So AMSR is an imager similar to Madras. The channel configurations are almost similar to that. And what we found is when we assimilate the sounder and imager together, so I think whoever planned the megatropics, their vision was very very good kind of thing. So they planned in such a way that in the same platform they are having both sounder and imager. So unfortunately, the imager stopped working. But when we did the experiment with a combination of sounder and imager, this is the numerical experiment, NWP experiment we did. So instead of Madras, we used the AMSR2. So the combination of that Saphir and AMSR, so we got the maximum input or the maximum positive impact due to the combination of this instrument. So in the future missions, if ISRO is planning, so we need both the sounder, microwave sounder and microwave imager in the same platform, so that we can get the maximum impact from this combination, as particularly in the NWP assimilation. So hence in the analysis and the forecast. So this is again the forecast impact we are showing. So here it is only for showing the Saphir. So this is the left figure. It is for 2019, 20 and 21. So as the Saphir instrument degraded, the impact was also very less. But if you see in 2018, so this is the left right panel. So 2018 Saphir, it is a single instrument compared to the ETOS or IRC or satellite wind or those things we are getting from multiple platforms. But Saphir was a single instrument from a single platform, and it helped to reduce the error 3.5% of error reduction in the forecast field. So Saphir is a very good instrument that, and all the NWP community is means recommending for the means repeat megatropics repeat mission kind of thing. So then, as a follow-on mission, now ISRO has launched that EOS 7, that is the microsat 2B. And if you see, the channel specifications are almost similar to that of Saphir, because this is also in the 183 gigahertz region of the spectrum. And only the difference is that Saphir megatropics, it was an inclined plane of 20 degree, but this instrument, this experimental mission microsat 2B, the orbit is 37 degree inclination, and there is an altitude difference in the altitude also. Saphir was around 850 or 860 kilometer altitude, that orbital altitude, but here it is in a very low Earth orbit, like around 450 kilometer. But if we can see, the channels are almost same in the same frequency range we are getting from the new instrument also. This new instrument data also we started getting from ISRO. So we got some 1 week data and we have analyzed those data. And we just compared the weighting functions of these two instruments for Saphir and Microsat 2B. And here the dotted line represents the Saphir channel, and the continuous line represent the new instrument, the Microsat 2B. So here also you can see that even if all the channels are in the same 183.31 gigahertz, but that plus or minus that there is a difference. The channel frequency, there is a slight difference in the in between these two instruments. So for the Saphir channel 1, you can see that the Saphir channel is slightly peaking slightly high in the atmosphere compared to the Microsat 2B. Similarly, channel 2 also, the Microsat 2B, the channel is peaking slightly lower in the atmosphere. That is one difference we noticed between the Microsat 2B channels. Even though almost the frequencies are in the same range, that peaking height is slightly means shifted down for the Microsat 2B. But that is again an advantage, as we have seen in one of the slides, the lowest peaking channel of Saphir, that was not present in any of the microwave humidity sounder, that has contributed maximum to the NWP assimilation system. Similarly, we are expecting that Microsat 2B, that the new instrument, that lowest peaking channel can contribute more than whatever the Saphir did. But I don't know how long this will continue, because this is an experimental mission, and the expected life, ISRO is expecting the lifetime of 1 year only. And being said all these, that we have to see that as we discussed, there are many satellites, but we have to see what is the gap in the satellite data we are getting. So current space-based microwave instrument constellation, if you analyze those things as means with respect to the equatorial crossing time. So as I told that at NCMR WF, we are running 4 assimilation cycle at 0, 6, 12, and 18 UTC. So we need the data, means we have to receive this real-time data within this assimilation cycle time. So 0 UTC means that assimilation window we are taking plus or minus 3 hours. So 0 UTC, we are taking the observation from previous day 21 UTC to current day 3 UTC. So we need to have that satellite data, or the satellite equator crossing time within this 6 hours. So if we get the data within these 6 hours, we can assimilate in the respective assimilation cycles. So if you see that here in 0 UTC, we have many, these lines shows the equator crossing time. So 0 UTC means it is 5:30 local time, and 6 UTC, that 11:30, like that it is marked. So if you see, we have a gap in the 6 UTC and 18 UTC time. And if you see in the 0 UTC and 12 UTC, we have lot of data. But the data gap is coming in the 6 and 18 UTC assimilation cycles. So in the future, that space missions, that space agencies has to see, they have to see that more coverage can be obtained during this 6 and 18 UTC assimilation cycle, so that the NWP models can also perform better than the current state. So this is one gap analysis that NCMRWF has done, and this feedback we have given to SAC ISRO, so that maybe they may consider in their future mission that equator crossing time may be matching with the that 6 and 18 means 6 and 18 UTC assimilation cycles. So this is what I want to say about the satellite data assimilation for NWP purpose. So I will stop here. Thank you. Thank you for listening.